Myself, Dr. Ranjita Sinha, Assistant Professor in the Department of Basic Science and Humanities, Physics Section, Asansol Engineering College, going to present the topic named Moment of Inertia. The subject name is Physics 1. Subject code is BS-PH101/201 according to MacOut, and it is under Module 1. Now the course outcome of this course. After the completion of the course, the students will learn to describe about the basic concepts of mechanics. Students can explain interference, diffraction, and polarization of light. Students can state the basic principles of laser and construction of ruby laser, helium neon laser, etc. Students can interpret about electromagnetic wave equation, dielectric and magnetic properties of materials. They can understand the basics of quantum mechanics. Students can discuss about the basics and applications of statistical mechanics. Now the introduction to moment of inertia. When a body is under the action of forces, it may have two types of motion. Number one, translatory motion, and number two, rotational motion. The translatory motion is caused by the application of a single force or the number of forces equivalent to a single force. To produce a given acceleration, the greater is the mass of the body, the greater is the force required. The property of a body of inertness or inability of a body to change by itself its position of rest or of uniform motion is called inertia. The measure of the inertia for translatory motion of a body is the mass of the body. It depends on the body's mass distribution and the axis chosen, with larger moments requiring more torque to change the body's rate of rotation. It is an extensive property. For a point mass, the moment of inertia is simply the mass times the square of the perpendicular distance to the axis of rotation. The moment of inertia of a rigid composite system is the sum of the moments of inertia of its component subsystems. Its simplest definition is the second moment of mass with respect to distance from an axis. Now the application of moment of inertia. Moment of inertia also appears in momentum, kinetic energy, and in Newton's laws of motion for a rigid body as a physical parameter that combines its shape and mass. The moment of inertia of a rotating flywheel is used in a machine to resist variations in applied torque to smooth its rotational output. This is the figure of flywheel. Flywheels have large moment of inertia to smooth out rotational motion. Next, tightrope walkers use the moment of inertia of a long rod for balance as they walk the rope. So this is the figure. Samuel Dixon crossing the Niagara River in 1890 using the application of moment of inertia. Spinning figure skaters can reduce their moment of inertia by pulling in their arms, allowing them to spin faster due to conservation of angular momentum. Now it can be explained here. Moment of inertia I is defined as the ratio of the net angular momentum L of a system to its angular velocity omega around a principal axis, that is I equal to L by omega. If the angular momentum of a system is constant, then as the moment of inertia gets smaller, the angular velocity must increase. So this is the explanation of this for the spinning figure scatters. They use the moment of inertia. This occurs when spinning figure scatters pull their outstretched arms or divers curl their bodies into a tuck position during a dive to spin faster. Now, four objects with identical masses and radii are acting down a plane while rolling without slipping. So these are the two figures here. Same, that is the identical masses. They are rolling. Now back to front, spherical cell. So this is first one is spherical cell here. Then solid sphere, this is. Then cylindrical ring, and at last solid cylinder here. So they are taking different time in rolling. The time for each object to reach to the finishing line depends on their moment of inertia. So they are reaching in different time, though they have identical masses and radii are. So it is depending totally on the moment of inertia of the bodies. Now, more about moment of inertia. The rotatory motion is caused and altered not by a single force, but by a couple or a number of forces reducible to a couple. A couple produces angular acceleration just as a force produces linear acceleration. To produce a given angular acceleration in a body, greater is the rotational inertia of the body, the greater is the couple required. The measure of the rotational inertia of the body is called the moment of inertia. So the measure of the rotational inertia of the body is called the moment of inertia. The inertia of a body in rotatory motion does not depend upon the mass alone, but also upon the distribution of the mass in the body about the axis of rotation. Moment of inertia plays the same role in rotational motion as does mass in linear motion. Now the expression of moment of inertia. Consider a body of mass m composed of a large number of small particles m1, m2, m3, etc. So these are m1, m2, m3, etc. These are the different different small particles, and m1 is at a distance r1 from axis AB, m2 mass is at a distance r2 from AB, and m3 mass is at a distance r3 from AB. So the moment of inertia of the particle m1, it is m1 r1 square. The moment of inertia of the particle m2, it is m2 r2 square, and for m3, it is m3 r3 square. And the moment of inertia of the body I about the axis AB is equal to the sum of moment of inertia of all the particles about the axis AB. So if m is the mass of the body and k is the radius of gyration of the body about AB axis, then we can write, I'm describing what is a radius of gyration later, I equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus dot dot going on. Now I equal to summation over m r square, and now the summation over m, that is capital M into k square. K is the radius of gyration. Now coming to radius of gyration, the effective distance of the particles of a body of its axis of rotation, it is called the radius of gyration, and its value depends upon the distribution of mass of the body and the position and direction of the axis of rotation. If the effective distance of the body consisting capital N particles, say having masses m each and being at distance r1, r2 dot dot rn from the axis of rotation AB, then it can be expressed as k equal to root over r1 square plus r2 square plus r3 square plus dot dot rn square by capital N. So this is the expression of radius of gyration. So the effective distance of the particles of a body of its axis of rotation is called the radius of gyration. Hence, we can define the radius of gyration as root mean square distance of the particles from the axis of rotation. Next, In order to know the moment of inertia of the body about a given axis, when its moment of inertia about some other axis is given, we can make use of the two important theorems. One is parallel axis theorem and the other is perpendicular axis theorem. So first we are describing what is parallel axis theorem. According to this theorem, the moment of inertia of a body about any axis is equal to its moment of inertia about the parallel axis through its center of mass plus the product of the mass of the body and the square of the distance between the two axes. So this is the theorem of parallel axis. Now we are considering a body of mass m having center of mass at C. Let the moment of inertia of this body about an axis passing through C and perpendicular to the plane of paper, it is IC. Let a particle of mass m, we are considering let a particle of mass m is at a distance x and the particle is at a distance x from O. So O is some point and from here it is at a distance x. The moment of inertia of this particle about an axis through O will be mx square, and that of the whole body is given by I equal to summation over m into x square. Now from the point P, so from the point P, drop a perpendicular PQ onto OC produced and join PC as triangle OPQ, as the triangle OPQ is a right angle triangle. So we can write OP square equal to OQ square plus QP square. So OP square equal to what? OQ square plus QP square. OQ square plus QP square. So OP square equal to OQ square plus QP square. Now OQ equal to what? OC plus CQ. OQ equal to OC plus CQ. So we have written this, and QP equal to QP square equal to CP square minus CQ square. QP square equal to QP square equal to CP square minus CQ square. So CP square minus CQ square. So QP square equal to CP square minus CQ square. Now we have just simply simplified this, and we have this OP square equal to OC square plus 2OC CQ plus CP square. So here written M in both sides, M OP square plus M OC square plus 2M OC dot CQ plus M CP square, like this. Now as OP equal to X and OC equal to R. Now OP equal to X and OC equal to R. So OC equal to R and OP equal to X. This is our assumption. So it is written here. So mx square in place of OP we are writing X. So a summation over mx square equal to OC equal to R. So summation over mr square plus summation over m CP square, this one, and this is 2m OC CQ. So 2mr CQ. Now we can write this as I equal to mr square plus IC, this is IC, 2r m into CQ. As the sum of turning moments of the weight of the particles about the center of mass is 0, so summation over MCQ is 0 as it is, though then we can, as it is, this is 0, so I equal to mr square plus IC, that is I equal to IC plus mr square. Now it is clear from the above relation, so this is the above relation, it is clear from the above relation that the moment of inertia of a body about an axis through the center of mass is less, and it is less than that about any other parallel axis. So here it is the moment of inertia, here IC, and here I is always greater than IC. So that we want to say that I is always greater than IC because mr square term is added to it. So the moment of inertia of a body about an axis through the center of mass. So this is the moment of inertia, IC. It is less, so IC is less and than any other parallel axis. So for any other parallel axis, it is moment of inertia is I. So I equal to IC plus mr square. Now, principle of perpendicular axis. The theorem states that the sum of moments of inertia of a plane lamina about two perpendicular axes in the plane of the lamina is equal to the moment of inertia of the lamina about an axis perpendicular to the plane of lamina and passing through the point of intersection of the first two axes. Now let the moment of inertia of a lamina about the perpendicular axis OX and OY be IX and IY respectively. Now this is the figure. If these axes OX and OY, which lie in the plane of the lamina, intersect each other at O, the moment of inertia about an axis passing through O and perpendicular to the plane of lamina will be given by I equal to Ix plus Iy. Consider a particle of mass m at P. We are considering one particle of mass m at P. The distance of the particle at P be x and y respectively. Now the distance of the particle at P, it is x and y respectively from x-axis and y-axis. So this is y and this is x. If the distance of P from O is r, then if the distance of P from this point O, if it is r, then Ix plus Iy equal to summation over my square plus summation over mx square equal to summation over mx square plus y square, and we can write it as summation over mr square. So I equal to what? Ix and Iy. So the moment of inertia about an axis passing through O and perpendicular to the plane of lamina, it is given by I equal to Ix plus Iy. Now describing the moment of inertia of a thin uniform rod. So this is the application, one of the application of moment of inertia, mathematical application. Now here that is some problem, numerical problem I'm discussing here. AB is a thin uniform rod. AB is a thin uniform rod of length small l and its mass is capital M. We are first finding out the moment of inertia about an axis passing through the center. So we are finding out the moment of inertia passing through the center, about an axis passing through the center, and it is perpendicular to its length. So this is the length of the rod and it is perpendicular. So y dash is perpendicular to its length, and we have to find out the moment of inertia passing through the center. The mass per unit length of the rod is m by l. So m is the total mass, l is the total length. So mass per unit length is m by l. And if we consider that is small length dx, then dx is the small element and it has mass equal to what? M by L into dx. M by L is per unit length mass. So for dx length, the mass is m by L into dx. Now, in order to get the moment of inertia of the whole rod about y dash, so about y dash, we should integrate the above expression between the limits x equal to minus L by 2 to x equal to plus L by 2, or integrate between the limits x equal to 0 to x equal to L by 2, and double it to include both halves of the rod. So what we are doing, we are going to find out the moment of inertia about an axis y dash which is perpendicular to its length, and here I equal to what? 2 into 0 to L by 2. So it is a half, and this is half portion and this is half, another half portion. So 2 into 0 to L by 2 m by L dx into x square. So this is m by L into dx into x square. Now integrating. So here 2 m by L, putting it outside, so x square dx integrate, and putting the value of the limits 0 to L by 2. So after calculation, we have the answer, that is m L square by 12. So this is the moment of inertia about an axis y dash passing the center. Next, what we are going to find out? We are going to find out the moment of inertia of the uniform rod about an axis passing through one end of the rod. Now, not through the center. Now, passing through one end, and we are taking y dash in one end of the rod, and it is also perpendicular to its length. Now, how we'll treat this? We will treat this here in this way, that is I equal to 0 to L m by L x square dx. So, if we integrate, what we will get? If we integrate, we will get that is m L square by 3. So, this is the moment of inertia of the thin uniform rod about an axis passing through the one end of the rod. Now, same result here we can find out using parallel axis theorem. Now, in parallel axis theorem, we know what? We know in parallel axis theorem, we know I equal to IC plus MR square. Now, we know IC is here what? ML square by 12. Here IC we have calculated, that is ML square by 12. Then what is the moment of inertia here at the end of the rod? That is equal to ML square by 12 plus MR square, that is M into L by 2 whole square. So here ML square by 12 plus ML square by 4. So add these two, ML square by 12 plus ML square by 4. That is your I here in the end of the rod. So if we add these two, according to parallel axis theorem, we will have the same result, that is ML square by 3. So if we know at the center, then using parallel axis theorem at y dash, what will be the moment of inertia? The moment of inertia in the center, that is ml square by 2, ml square by 12, that we have calculated earlier, plus this distance, that is L by 2, this is from this center to this, it is L by 2. So m into L by 2 square. So ultimately ml square by 12 plus m into m L by 2 square. So if we add this two, again we will get ml square by 3. So this is the moment of inertia at the end of the rod. So in this way, using parallel axis theorem, we can also find out the same. So this we have discussed the moment of inertia of a thin rod through its center and through one end. And what we have, what is the summary of today's lecture? That we have discussed what is moment of inertia. We have discussed different applications of moment of inertia. Then two theorem are there. That is parallel axis theorem, perpendicular axis theorem. We have also explained what is radius of gyration. So theorem of parallel axis we have explained, theorem of perpendicular axis we have explained, and one mathematical calculation for the calculation of the moment of inertia of a thin rod also we have discussed at the center of the rod and also at the end using parallel axis theorem. So today up to this for moment of inertia.